So let's talk about quantum mechanics. First, list out the standard books of quantum physics.
When it comes to standard quantum physics references, a few classics stand out. You've got Principles of Quantum Mechanics, Dirac, which is a very formal foundational approach. Then Quantum Mechanics by Cohen, Tanuji, Dew, and Lalo is a detailed and comprehensive two-volume set. For a modern approachable path, Introduction to Quantum Mechanics by David Griffiths is beloved by students. And if you're looking for a more in-depth theoretical approach, you can't go wrong with Modern Quantum Mechanics by J.J. Sakurai. Lastly, for a more historical and conceptual deep dive, there's the Feynman Lectures on Physics, Volume 3 by Richard Feynman. These form a solid backbone of the field.
So, first, let's tackle that Feynman book. Can you tell me how Feynman introduces and discusses the quantum physics?
Feynman's style is famously intuitive and conceptual. In Volume 3 of his lectures, he opens by emphasizing the radical departure quantum mechanics represents from classical intuition. He introduces the core idea of quantum behavior using the famous double slit experiment and explains that particles exhibit both wave-like and particle-like properties. He avoids heavy math at first, focusing on thought experiments and the logical consequences of quantum rules. Then, step by step, he builds in the mathematics, like probability amplitudes and the superposition principle, always tying them back to physical intuition. In short, he demystifies the weirdness with clarity and charm.
So, you mentioned about that thought experiment. How does Feynman discusses that?
Feynman presents the double slit experiment as the ultimate gateway to quantum mechanics. He asks Jen firing electrons one by one at a barrier with two slits and observing where they land on a screen. If you only looked at the final spots, you might think electrons are particles, but as you let many electrons pass, you see an interference pattern, something waves would create. He drives home the paradox. When you try to measure which slit the electron went through, the interference disappears. In short, he shows that quantum systems don't behave like classical objects, and our attempts to measure them change the outcome.
That's the key idea. Our attempts to measure them changes the outcome. What's the that leads to?
That's the heart of the observer effect and the principle of quantum measurement. Feynman and quantum theory shows that when you measure a quantum system, you don't just passively look. The act of measurement collapses the wave function. Before measuring, a system exists in a superposition of possible states. When you measure, the system chooses a definite outcome. This is what leads to the probabilistic nature of quantum mechanics. Instead of predicting exact outcomes, you predict probabilities. It's a major shift from classical determinism and is central to everything quantum.
Okay, then one thing Feynman discusses about this thought experiment. What next he discusses in more detail.
After laying out the double slit experiment, Feynman dives deeper into the mathematics of quantum behavior. He introduces probability amplitudes and the idea that you add these complex amplitudes for all possible paths to predict outcomes. He introduces the famous path integral idea. Particles explore every possible path and you sum over them. He discusses how this leads to the Schrödinger equation, the key equation that governs quantum systems. From there, he explores atomic structure, spin, and other phenomena, always balancing theory with intuition.
Okay, before that, can you list out the content of that book, Feynman Lecture Volume 3, Quantum Mechanics? What are the chronology approach that he uses to teach that?
Feynman begins by showing the puzzle, the double slit experiment that reveals wave particle duality. From there, he builds intuition for superposition, probability amplitudes, and the necessity of complex numbers. Once that foundation is set, he introduces the Schrödinger equation as a central mathematical tool. He then applies it to atomic systems, introduces spin and angular momentum, and explores how measurement affects systems. Essentially, he starts with conceptual mystery, then moves through the formalism, all the while anchoring theory in practical examples.
Any key takeaway we can take from that book?
The biggest takeaway is that quantum mechanics defies classical intuition. Nature behaves probabilistically. Feynman emphasizes that to understand quantum reality, you have to let go of everyday expectations. Measurement changes outcomes, particles act like waves. The key lesson is that the world at its smallest scale is governed by probabilities, amplitudes, and rules that are fundamentally different from classical physics, and yet beautifully consistent.
Okay, so there is a famous book by Claude and Claude. Can you tell me? I think there are three volumes of that book. I only mentioned about one first author, something like that. Can you?
I think you're referring to the classic quantum mechanics series by Cohen Tanuji, along with co authors Bernard Dew and Frank Lelot. Yes, it's a 3 volume masterpiece. The first volume is usually what people start with. It covers the fundamental postulates, wave mechanics, and basic applications. Then the subsequent volumes dive into more advanced topics like angular momentum, approximation methods, scattering theory, and relativistic quantum mechanics. It's an incredibly thorough, mathematically rich series, definitely a cornerstone of quantum education.
Okay, tell me the approach he used to teach that vast quantum physics.
Cohen Tanuji and his co authors take a meticulous layered approach. They begin with the postulates of quantum mechanics, ensuring you understand the foundational rules, states, operators, measurements. Then they systematically introduce wave mechanics, formalism in Hilbert space, and operator methods. They emphasize both physical intuition and mathematical rigor. As you progress, they add complexity, angular momentum, approximation techniques, scattering, and eventually advanced topics like relativistic quantum mechanics. Each topic builds on the last, and they provide extensive examples and exercises to solidify understanding.
Okay, now there is another book by R. Shankar. How did he discusses quantum physics?
R. Shankar's Principles of Quantum Mechanics strikes a balance between rigor and accessibility. He starts with the basic postulates and mathematical tools. Linear algebra is key. He builds from the ground up, introducing the Schrödinger equation, operators, and the formal structure of quantum mechanics. Shankar also likes to offer historical context and motivations, so you see why the theory developed as it did. As you advance, he covers topics like angular momentum, perturbation theory, and identical particles. His style is methodical, peppered with clear examples, and aimed at giving you both deep understanding and practical problem solving skills.
Okay, now the volume 3 of theoretical physics course from Landau and Lifis. Can you tell me their approach? I think it's a non-relativistic.
Exactly. Landau and Lifshitz's quantum mechanics non relativistic theory is famously concise and rigorous. They assume you're comfortable with advanced math. They begin from the most fundamental principles, states in Hilbert space, the Schrödinger equation, and rapidly build up to solving key problems. Their style is highly theoretical, abstract, formal, and elegant. They cover everything from the uncertainty principle to angular momentum, perturbation theory, and scattering. Their approach is no nonsense, minimal in handholding, and aimed at developing mastery through deep, direct problem solving.
Okay, there is another book by Leonard Sif.
Leonard Susskind's books, he's known for making complex ideas accessible. In his Theoretical Minimum series, for example, he approaches quantum mechanics by building from first principles, but always with a conversational tone. He introduces the basics of state vectors, operators, and measurements, and he wants you to grasp the conceptual why as much as the how. He uses clear examples and thought experiments, and he emphasizes that you don't need excessive formalism to start getting it. His approach is understand the core ideas, then work toward the math.
I think I mentioned about Leonard Sif book, I think, not Suskind. Although Suskind has also a book.
Ah, you likely mean Quantum Mechanics by Albert Messiah. It's a classic. Messiah's approach is thorough and systematic. He starts from the postulates, develops wave mechanics, and then moves to operator formalism. His presentation is mathematically rigorous but clear, covering foundational principles, approximation methods, angular momentum, and scattering. His style is logical, step by step, and aims to build a complete and solid foundation. A true comprehensive course in quantum theory.
Can you discuss that part where he start from the postulate, develop wave mechanics, and then moves to operator formalism?
Messiah takes you on a structured journey. He begins by laying out the core postulates of quantum mechanics, things like the wave function, superposition, and measurement. He then develops wave mechanics, starting with the Schrödinger equation and exploring solutions for simple systems, like the particle in a box or the harmonic oscillator. After giving you intuition with wave functions, he transitions to operator formalism, highlighting the power of abstract operators, eigenvalues, and commutation relations. In doing so, he shows how the abstract operator approach generalizes and simplifies solving quantum systems like angular momentum or spin. It's a smooth progression from concrete wave methods to the more general operator based formalism.
Okay, I think there are a series of Nobel prizes that goes to the development of quantum physics. Can you start from scratch and tell every contribution they have made?
The Nobel timeline is pretty rich, so let's hit some key milestones. In 1918, Max Planck was awarded for originating quantum theory. He introduced the idea of quantized energy. In 1922, Niels Bohr won for his atomic model, explaining electron orbits and quantized energy levels. In 1929, de Broglie got recognized for wave particle duality. Then, 1932, Heisenberg was honored for the uncertainty principle. Schrödinger and Dirac shared it in 1933 for their wave mechanics and quantum equations. Later, in 1954, Born was recognized for his probabilistic interpretation. And the list goes on. Feynman, Schwinger, and Tominaga for quantum electrodynamics in 1965. These Nobels mark key steps: quantization, atomic structure, uncertainty, wave equations, and the quantum field theory framework.
I think from your perspective, what is the most interesting turn for this thing?
From my perspective, one of the most fascinating turns is when quantum mechanics moved from describing single particles to quantum fields. Early on, it was about atoms and electrons, but when people like Dirac and later Feynman extended the theory to fields, like QED and QFT, it was revolutionary. Suddenly, particles were excitations of fields, interactions were quantized, and the framework extended to all fundamental forces. That shift to field theory unified so much of physics. It's where quantum mechanics started speaking the language of the entire universe.
Okay, QFT is the more broader version of QM, and then where we talk about many particle system, their Hamiltonian operator, Schrodinger equation, and see the dynamics, and we include fields also.
Exactly. Quantum field theory takes the principles of quantum mechanics and applies them to fields rather than just particles. In QFT, each type of particle is an excitation of a corresponding field. The Hamiltonian governs the dynamics of these fields. The Schrödinger equation is generalized to a field equation, often using the formalism of the Lagrangian and path integrals. In this broader framework, you can describe interactions, like electromagnetic or nuclear forces, and you naturally account for particle creation and annihilation. So QFT is the natural evolution, treating many particle systems and fundamental forces in a unified field-based way.
And in QFT, how do we quantize things there? What are the approaches they have made? Because quantization is the heart of this QM?
In QFT, quantization is done by promoting classical fields to operators. One key method is canonical quantization. You treat the fields and their conjugate momenta, like position and momentum in quantum mechanics, imposing commutation or anti commutation relations. Another approach is the path integral formalism pioneered by Feynman. Here, you sum over all possible field configurations, weighted by the exponential of the action. Both methods yield creation and annihilation operators, allowing particles to emerge from or vanish into the vacuum. In short, QFT quantizes fields themselves, making particles mere quanta of those fields.
Okay, the main idea is that QFT quantize the field, like Klein Gordon field, one example, and making the particle quanta of particle from that.
I'm sorry, but you've hit the
So in QFT, fields are quantized themselves, like Klein Gordon field, and then making particles quanta of those fields. That's the key idea.
Exactly, you've got it. In QFT, fields like the Klein Gordon field for scalar particles or the electromagnetic field for photons are treated as fundamental quantum entities. When you quantize these fields, you essentially break them down into discrete excitations, and these excitations are what we identify as particles. This perspective unifies the concept of particles and forces, and it allows us to describe interactions and particle dynamics in a very elegant and comprehensive framework. It's definitely a beautiful and profound shift from the older quantum mechanics perspective.
Okay, then.
Absolutely. It's such a fascinating area, and there's always more to explore, whether it's delving deeper into specific interactions or looking at more complex field theories. If you ever want to dive into any particular aspect, I'm always here to chat.
What about this observation in quantum mechanics?
Observation in quantum mechanics is a really intriguing topic. Essentially, it revolves around the idea that measurement plays a fundamental role in determining the state of a quantum system. Before measurement, a system exists in a superposition of possible states. Once you measure it, the wave function collapses to a definite state. This leads to the famous observer effect, where the act of observing alters the outcome. It's a central puzzle that's driven a lot of the philosophical discussions around quantum theory. It's definitely one of the most fascinating and sometimes perplexing aspects of the field.
So when we solve the two-body hydrogen atom problem in quantum mechanics, because that is the first solution they have done, then in the last solution part, they have got the results was what?
When solving the hydrogen atom in quantum mechanics, the fundamental outcome is that the electron's energy levels are quantized. We end up with discrete energy states corresponding to different quantum numbers. The solutions give us the well known orbitals like the s, p, d, and f orbitals, each with their own specific shapes and energy levels. Ultimately, what comes out of the solution is that the electron in a hydrogen atom can only occupy certain allowed energy levels, and these are determined by the principal quantum number and other quantum numbers. This quantization explains the spectral lines we see in the hydrogen atom, and is a cornerstone of quantum mechanics.
So what about this? I think only the energy thing is very important. Basically, whatever the interaction picture we capture, either spin orbit coupling or the dynamics through Coulomb potential or the external field, we often conclude that we are just getting the energy or the probability.
Absolutely, that's spot on. At the heart of it, quantum mechanics often boils down to how energy levels shift and how probabilities are distributed. Whether we're looking at spin orbit coupling, the effects of external fields, or subtle interactions like the fine structure of the hydrogen atom, the key takeaway is often how these factors alter the energy levels and the probability distributions of the electron, the position, and momentum. In essence, all these interactions help shape the energy landscape and the probabilities we calculate, which then leads to the observable phenomena we see. It's all interconnected in a beautifully intricate way.
Okay, I think everything we read and understanding the language of Hilbert space there. So we define state vector, and that state vector, whatever the operator we want to do and interact with the state, we have to write down the operator, and then evolution is governed by Schrodinger equation, and then in case of time dependent but energy eigenvalue also give, and then there is a measurement outcome.
Exactly. The whole framework is built on the idea of the Hilbert space, where each state vector represents a possible state of the system. When we apply operators, we're essentially probing or transforming these states. The time evolution is governed by the Schrodinger equation, and for time dependent scenarios, we consider how this state changes over time. And indeed, when we measure the system, the outcome is determined by the probabilities associated with those eigenstates. It all ties together into a beautifully coherent and elegant structure.
So if we do not convert if we do not take operator into the Schrodinger equation, will the Schrodinger equation will be simplified?
Yes, definitely. When we consider the Schrodinger equation in its most fundamental form, we can think of it as describing the time evolution of the wave function directly. If we don't introduce operators, the equation essentially focuses on how the wave function evolves in time under the influence of the Hamiltonian, which is usually represented as an energy operator. In that simpler form, the equation J tells us how the wave function changes with time, governed by the potential energy and the kinetic energy terms. So in a sense, the equation becomes more straightforward, focusing purely on the wave function's evolution rather than the additional complexity of operators acting on states. It definitely simplifies the picture, at least conceptually.
And when we introduce that,
When we introduce operators, we bring in the full power of the formalism. Operators let us explore observables like position, momentum, angular momentum, and energy in a more structured way. They allow us to find eigenvalues and eigenstates, and they help us understand how measurements affect the system. Essentially, operators let us connect the abstract wave function to measurable quantities, and that's where the deeper insights and the full richness of quantum mechanics come into play.
okay, then I was thinking about this one very key idea, and the fact that you think it's very interesting to observe in quantum physics.
Absolutely. There are so many fascinating aspects in quantum physics. One of the most captivating ideas is the concept of quantum superposition and entanglement, the way particles can exist in multiple states at once until measured, and how entangled particles can instantaneously influence each other over large distances is truly mind bending. It challenges our classical intuitions and opens up a world of possibilities. It's that blend of deep theoretical complexity and profound philosophical implications that makes quantum physics endlessly intriguing.
Okay, so for the hydrogen atom case, there are electron and proton. So those are basically there because of the Coulomb potential they have acted. When we simplify those problem in the quantum physics, so we wrote down that there is a two particle having mass charge and their separation between them, and they evolve in time with the Coulomb potential. We wrote down the Hamiltonian of the system and the boundary conditions that would specify its the Coulomb range of that Coulomb potential. And we say that there is a spherically symmetric potential, and we get the radial part of the solution, only the radial dependence, and we get the discrete energy level.
Exactly, you summed it up beautifully. In the hydrogen atom, the electron and proton interact via the Coulomb potential, and by considering their masses and charges, we can write down the Hamiltonian for the system. By exploiting the spherical symmetry, we separate the problem into radial and angular parts. The angular part leads us to spherical harmonics, and the radial part gives us the radial wave functions. Solving these equations, we end up with discrete energy levels, which corresponds to the quantized orbitals. It's this quantization that leads to the well-known spectral lines of hydrogen. It's a perfect example of how quantum mechanics beautifully explains atomic structure.
But you missed that boundary condition part that I explained. Is that true, that how they design that boundary condition?
You're absolutely right. The boundary conditions are indeed crucial. For the hydrogen atom, we typically require that the wave function remains finite at the origin and that it vanishes at infinity. These conditions ensure the physical acceptability of the solution. The radial wave function, for example, must be well behaved at r equals 0 and must go to 0 as r approaches infinity. These boundary conditions, combined with the spherical symmetry, really help us pin down the quantized energy levels and the allowed state. So the boundary conditions are definitely a fundamental piece of the puzzle in arriving at the correct solutions.
Okay, can you make conclusion what we have discussed and what impact it should have from our discussion?
Absolutely. To sum up, we've explored how quantum mechanics fundamentally describes the behavior of particles, like in the hydrogen atom, by quantizing energy levels through the interplay of wave functions, potentials, and boundary conditions. We've also touched on how operators and Hilbert space form the backbone of quantum theory, allowing us to connect abstract states to measurable quantity. The impact of this understanding is profound. It explains atomic structure, the nature of light and matter, and even the fundamental forces in the universe. It also opens doors to advanced fields like quantum field theory, entanglement, and quantum computing. Overall, our discussion highlights how quantum mechanics not only explains the micro world, but also sets the foundation for countless modern technologies and theories.
Can you give a highlight on 2026, 2025 Nobel in physics that was actually based on macroscopic quantum mechanical tunneling and the backbone for quantum computing?
In 2025, the Nobel Prize in Physics was awarded to John Clark, Michel Devoret, and John Martinez for their groundbreaking work on macroscopic quantum tunneling and energy quantization in superconducting circuits. Their experiments in the 1980s demonstrated that entire circuits could behave quantum mechanically, paving the way for superconducting qubits, which are now central to quantum computing. This discovery truly forms the backbone of modern quantum technology.
Can you explain that concept in terms of the quantum language?
Absolutely. In quantum terms, macroscopic quantum tunneling refers to the phenomenon where large scale systems like superconducting circuits exhibit quantum behaviors that are typically only seen at microscopic scales. In superconducting circuits, electrons pair up to form what we call Cooper pairs, and these pairs can tunnel through energy barriers even if they don't have enough energy to overcome them classically. This tunneling effect allows the system to be in a superposition of states, meaning that the circuit can exist in multiple states simultaneously. This principle is at the heart of quantum bits or qubits, which can represent both 0 and 1 at the same time. This enables quantum computers to perform complex computations much more efficiently than classical computers. In short, macroscopic quantum tunneling bridges the gap between quantum mechanics and real-world quantum technology, making it a cornerstone for the development of quantum computing.
Uh, what one major idea that led to framing such a strong quantum mechanical macroscopic theory that I think it's just a proper setup and proper calculation that leads to this interesting thing.
Absolutely. One of the key ideas that really propelled the understanding of macroscopic quantum phenomena was the concept of superconductivity itself and the formation of Cooper pairs. When researchers realized that these pairs of electrons could move through a lattice without resistance, it opened up the door to quantum effects on a macroscopic scale. The proper setup, including the design of superconducting circuits and the precise control of parameters like temperature and magnetic fields, allowed scientists to observe quantum effects in these large systems. It was this combination of theoretical insight and meticulous experimentation that paved the way for the development of quantum computing and the understanding of macroscopic quantum phenomena.
It's like a parameter like temperature and magnetic field control in that superconducting circuit.
Exactly, temperature and magnetic field play crucial roles. For instance, cooling the superconducting circuit down to extremely low temperatures is essential to achieve superconductivity. At these low temperatures, the material's resistance drops to zero, allowing electrons to form Cooper pairs and move without scattering. Meanwhile, applying a magnetic field can help manipulate the quantum states of the qubits and control their behavior. All of this precise control over environmental parameters is what makes the macroscopic quantum effects stable and reliable, forming the backbone of robust quantum computing technologies.
But how they control that system, because they form that Cooper pair, that tunnel, but did they able to control that pair?
Yes, they can definitely control it. Researchers use a combination of advanced techniques. For example, they use carefully tuned microwave pulses to manipulate the quantum states of the qubits, allowing them to control the tunneling rates and the coherence of the qubits. Additionally, they use magnetic flux control in superconducting loops, which lets them adjust the energy levels and the tunneling barriers precisely. They also use carefully designed materials and circuit architectures to ensure that the quantum states remain stable and coherent for longer periods. All these control methods together make it possible to harness macroscopic quantum effects in a reliable and controllable way.
Okay, thank you.